All right, let's just dive right into this. Welcome to today's Explainer, where we're going to unlock what I think is one of the most brilliant visual puzzles in all of computer science. If you've ever looked at a massive tangled string of Boolean logic and thought, there just has to be an easier way to simplify this, well, you are in exactly the right place. Today, we're taking a masterclass in the Karnaugh Map. It's this absolutely ingenious grid system that lets us effortlessly compress clunky, complicated computer circuitry down into its most elegant, efficient form, literally just by drawing a few simple boxes.
Here's our roadmap for today. First, we'll ask, why simplify Boolean logic? Then we'll introduce the Karnaugh map itself. Third, we'll go over the rules of grouping. After that, we're going to start thinking in 3D with something called the torus. And finally, we're taking on the 4-input boss level.
So, Section 1. Why simplify Boolean logic? Let's talk about the real-world stakes here. You see, there's this direct bridge between abstract math and actual physical hardware. Those Boolean expressions, they describe real electric circuits and logic gates inside your computer. So if we can shrink down those expressions, we literally reduce the number of physical parts we need to build. And that's a huge deal. It physically shrinks the circuit, which, as you can guess, immediately lowers manufacturing costs. Plus, fewer components just naturally use less power. Oh, and a simpler circuit, it actually executes instructions way faster because it doesn't have to fetch as many variables from memory. So, simplifying this logic isn't just some abstract academic exercise. It literally makes our tech smaller, cheaper, greener, and quite a bit faster.
All right, moving to Section 2, introducing the Karnaugh Map. We're going to start at the basic 2-input level.
Let's look at a really foundational example. Imagine a circuit described by this slightly clunky expression, A and B, or A and not B. To solve this, we just set up a really simple grid. We put variable A across the top, variable B down the side. Now we tackle this expression by breaking it apart at the OR. First up, A and B. We find the cell where both A and B are 1, and boom, we drop a 1 right in that box. Next up, A and not B. So we look for where A is 1, but B is 0, and we place our second 1 right there. Now remember, we only ever put 1s in these cells. Leaving the rest blank is perfectly fine. Actually, it's exactly what we want.
Now check this out. Notice how both of those 1s stack perfectly in the column where A is 1. The state of B, whether it's a 0 or a 1, literally has 0 impact on our final outcome. Because we group them visually like this, we can instantly see that our clunky B4 expression simplifies down to just a single, incredibly elegant variable, just A. Just like that, you've conceptually wiped out an entire physical logic gate from existence.
Moving right along to Section 3, the rules of grouping. We're stepping it up to 3-input maps and introducing gray codes.
Okay. Let's toss a third variable into the mix. We're going to solve this expression, not C and B, or A and B or C. Since we've got 3 variables now, we group A and B across the top, and we drop C down the side. We fill out our 1s in the grid where the conditions are true, same as before. But I want you to pay really close attention to the headers across the top. Look at the sequence, 0, 0, 0, 1, 1, 1, 1, 0. You catch that? It's kind of odd, right? We are definitely not counting up in standard binary.
That highly specific sequence is called gray codes, and this is absolutely vital. Think about it. If we counted normally, going from 0, 1 straight to 1, 0, 2 digits would flip at the exact same time. The first goes 0 to 1, the second goes 1 to 0. Gray codes are special because they ensure that only a single, lonely digit changes as you hop from one heading to the next. Why does that matter? Well, this entire Karnaugh Map visual puzzle relies on adjacent cells sharing a common variable so we can spot patterns. Without gray codes, the matching variables wouldn't sit next to each other, and the whole system would just fall apart.
So, with our board properly prepped using gray codes, we need to group our ones. And there are strict, unbreakable rules for drawing your boxes. Rule number 1, boxes have to be rectangles or squares. No diagonals, absolutely no way. Rule 2, you can only box the ones. Rule 3, the number of ones in a box must be a power of 2. So you can group 1, 2, 4, 8, or 16 of them. You can't just draw a box around 3 ones or 6 ones. It's got to be 2 to the power of n. And finally, Rule 4, which is how we get the smallest number of groups overall. Overlapping your boxes is not just allowed, it's actually highly encouraged. Now, here is the secret sauce. This is how we analyze those boxes once they're drawn. I want you to treat this quote like a personal mantra. Seriously, repeat it in your head every time you draw a box. If the digit for the variable in the heading stays the same, keep the variable. If the digit changes, discard the variable. Let's actually test out that mantra on the map we just built. If we follow our rules, we can grab all our ones using just 2 overlapping boxes of 4. One box handles that bottom horizontal row, and a second box grabs the square of 4 right in the middle. Let's look at the square box first. Glancing at the top headers, variable a changes from a 0 to a 1 across that box. So mantra says, discard a. Down the side, variable c goes from 0 to 1. Discard c. But look at variable b. It stays a solid 1 in both columns covering this box. So we keep b. Now we do the exact same thing for the bottom horizontal box. Variables a and b change as we move across those 4 columns, so toss them out. But c? C stays a 1 across that entire bottom row, so we keep c. And just like that, our massive, messy equation is sliced all the way down to a beautiful, clean b or c. Oh, and a quick side note here. You might be wondering, does it matter if I write b or c versus c or b, depending on which box I looked at first? No, not at all. That is what's known as the law of commutation. It basically just means the order of expressions on either side of an OR operator doesn't matter one bit. They are functionally identical.
All right, Section 4, Thinking in 3D, the torus. This is where we really expand the map.
So up to this point, we've kind of been treating this Karnaugh map like a standard flat piece of paper. But actually, scratch that. To really master this, you have to realize it's not a flat 2D grid at all. Mathematically speaking, it's a 3D, continuous, donut-shaped object known as a torus. Yes, you heard me right. The secret to advanced computer science logic is literally donuts. Because of how we set up those gray codes earlier, if you slide off the left edge of the map, you instantly pop back out on the right edge. Same goes for the top, it directly touches the bottom. And this continuous 3D shape gives us a real game changer, the wraparound rule. Look at those 2 ones stranded way over on the far left column and the 2 stranded on the far right. On a flat piece of paper, you'd be stuck drawing 2 separate, inefficient boxes. But on our torus, the left edge touches the right edge. Those 4 ones are actually right next door to each other. We can draw a single, wraparound box that grabs all of them at once for maximum simplification.
Okay, we are ready. Section 5, the 4-input boss level. Let's master this complex map.
We are fully geared up. It's time to take everything we've learned, every rule, every gray code, every 3D donut trick, and throw it at a massive, incredibly expensive 4-variable problem. Here is our monster boss-level expression. Not A and B and C and D, or not A and B and C, or not D. Yikes. So, 4 variables, A, B, C, and D. That means a 4x4 grid, giving us 16 possible states. We've got A and B on top, C and D on the side, completely sequenced with our gray codes. We've dropped in our ones based on the expression. Now, look at this daunting board. How on earth do we draw the fewest, largest boxes here?
Well, first, let's hunt for the absolute biggest power of 2 we can find. Remember our torus rule? Look at that. There's a massive 8-cell box wrapping around the entire top and bottom rows. Okay, let's chant our mantra. Across those 8 cells horizontally, variables A, B, and C are all over the place. They change digits, so we toss them. But look at variable D in the side heading. For the top and bottom rows, D stays locked at 0. Because it's a 0, we keep the not version of the variable, so we've got not D. Awesome. Now we still have 2 lonely 1s left in that second row. We'll draw a 2-cell box around them. Apply the mantra again, D changes from 1 to 0, so D is gone. But A stays 0, B stays 1, and C stays 1. So we keep not A and B and C. And there it is, the final victory of today's explainer. We started with this incredibly clunky, incredibly expensive, original boss expression that would have needed a huge, messy array of physical logic gates. But by mapping it out, using gray codes, bending our minds into 3D, and just sticking to our mantra, we visually compressed the whole shebang down to not D or not A and B and C. We literally just optimized this circuit into a perfectly elegant solution.
So I want to leave you with one final thought to chew on. We just did this by hand, for 4 variables. But the principles you learned today, they are the exact fundamental building blocks used to streamline the hardware running our modern world. If drawing a few simple boxes on a grid can save this much computing power, space, and energy in just one single equation, how many billions of logic gates do you think these exact techniques are silently optimizing inside the very device you're watching this on right now? Pretty mind-blowing, right? Thanks so much for learning with me today, and keep exploring the incredible logic that powers our world.